Thank you, Arya. Very good evening to all. Today is 6th day of Guruvachan2023, the multidisciplinary international webinar series being hosted by R. Shankar Memorial SNDP Yoga Arts and Science College, Pune. I am extremely delighted to welcome all the participants to today's technical session conducted by Mathematics Department. We are extremely fortunate to have the presence of our eminent resource person, Dr. Mookambika A.P, Assistant Professor of Mahatma Gandhi Government Arts College, Mahe, Pondicherry University. Her academic credentials including PhD from Annamalai University with the topic A Study of on Generalized Closed Sets in Nano and Notoscopic Nanotopological Spaces and the publication of more than 10 papers in many reputed international journals shows her continuous pursuit of knowledge and excellence. I extend my warm welcome to you, ma'am. I extend my heartfelt greeting to our principal, Dr. Sujesh C.P., the charismatic president. I would like to express my deep sense of gratitude for the unceasing support and guidance preferred by the principal. Welcome, sir. I also welcome the IPSC coordinator, Ms. Chandini PM, the webinar coordinator, Dr. Bhavya B, chair of the session, Dr. Vinny K, assistant professor, Department of Physics, Ms. Nandita Yuva, assistant professor, Department of English, and also the teaching staff, students, as well as the participants from other institutions to today's technical session. I welcome one and all. I welcome the encouraging and empathetic Dr. Vinny K, assistant professor, Department of Physics, to chair today's session. Over to you, ma'am. Thank you.
Thank you, Anakshara. A very fine good evening to one and all present over here. Today, we are blessed with the presence of eminent personality Dr. Mookambika A.P, Professor from the Central University, Pondicherry. I'm extremely happy to share this session because Dr. Mookambika A.P is my teacher, my guru, and she taught me mathematics when I was doing my graduation from Mahatma Gandhi Government College. So happy to see you, ma'am, here on this platform. Thank you so much for being here and a happy welcome. And the topic that we are going to deal with is the geometrical interpretation of Riemann integral. So I think all of you are familiar with this integration. From 11th standard onwards, we have started studying this integration. But this Riemann integration is not much different from other integration. But when we are given a function, for example, if you are given an x square, you can do it because we have a particular formula for that. For example, x raised to n plus 1 by n plus 1, we have a separate formula. Same way, if you are asked to do the sine function, similar way you can do it. But there are some other functions which we cannot do it in the simple manner. There we have to check whether this is integrable or not. So here comes the importance of this Riemann integration. To know more about this integration, to learn the geometrical interpretations and all, I welcome our esteemed guest, Dr. Mookambika A.P. Now, shall we start now?
Vinny, can you hear me?
Oh, ma'am. What is the ma'am? Yeah, okay, ma'am. Let's start now.
Oh. Good evening to all. Our topic is geometrical interpretation of Riemann integral. Geometrical interpretation of Riemann integral. Important definition of Riemann integration is: first point is partition of a closed interval. Partition of a closed interval. Second one is refinement of partition. Third, subintervals and length of subintervals. Next, upper sum and lower sum. Upper and lower Riemann integral. Last one is Riemann integration. Riemann integral. Here we discuss how to find the area under the curve between two points. Part B, where A and B are real numbers. Here A less than B. Okay. Here we consider a closed interval A comma B, where A and B are real numbers and A less than B. We can find infinite number of points between A and B. Okay. We can find infinite number of points between A and B. Here, first we consider only finite number of points x0, x1, etc., xn. Here we consider only finite number of points x0, x1, etc., xn, where x0 less than x1, less than x2, less than x3, so on less than xn, where A is equal to x0 and B is equal to xn. Here, x0, x1, etc., xn are called the partition points of closed interval A comma B. x0, x1, etc., xn are called the partition points of closed interval A comma B. Here, P is equal to, set up for these partition points, that is P is equal to x0, x1, etc., xn is called the partition of the closed interval A comma B. Is called the partition of the closed interval A comma B. Here an example: x0, A is equal to x0, B is equal to x10. Here x0, x1, x2, so on x10 are said to be partition points. x0, x1, x2, so on x10 are said to be partition points, and set upon these partition points, we say here denoted by capital P, it is a partition of closed interval A comma B. Set upon these partition points, we say partition of a closed interval A comma B. For an example, here we consider a closed interval 0, 5. Here 0, 1, 3, 5 are called partition points. 0, 1, 3, 5 are called partition points, and P1 is equal to set 0, 1, 3, 5 is a partition set or partition of the closed interval 0, 5. 0, 1, 3, 5 are called partition points, and P1 is equal to set 0, 1, 3, 5 is a partition set. Another example, same closed interval 0, 5. Here P2 is equal to set of all 0, 1, 2, 3, 4, 5. Here 0, 1, 2, 3, 4, 5. 0, 1 is 0, 5 is a closed interval 0, 1, 2, 3, 4, 5 are called partition points. This set is called partition set or partition of a closed interval 0, 5. Here P1 is equal to set 0, 1, 3, 5 and P2 is equal to set 0, 1, 2, 3, 4, 5. Here P2 contains all the points of P1. Then P1 is a subset of P2. P1 is equal to set 0, 1, 3, 5 and P2 is equal to set 0, 1, 2, 3, 4, 5. Here P1 is a subset of P2 since P2 contains all the points of P1. Next definition, important definition is refinement of a partition. Refinement of a partition. If P1 and P2 are two partitions of closed interval A, B. P1 and P2 are two partitions of closed interval A, B and P1 subset of P2. Then P2 is called a refinement of partition P1 on closed interval A, B. Here P1 and P2 are partition of closed interval A, B. P1 subset of P2, then P2 is called a refinement of partition P1 on closed interval A, B. Or P2 is finer than P1. P2 is finer than P1. For an example, that P1 is equal to set 0, 2, 4, 6 and P2 is equal to set 0, 1, 2, 3, 4, 5, 6 are partition of a closed interval 0, 6. P1 and P2 are the partition of the closed interval 0, 6. Here P1 is a subset of P2. Since P2 contains all the elements of P1, therefore P1 is a subset of P2. Then P2 is called refinement of partition P1 on closed interval 0, 6. Here P2 is called refinement of P1 on closed interval 0, 6. Okay, next. If P1 and P2 are two partitions of closed interval A, B, then P1 is, we know that P1 is a subset of P1 union P2 and P2 is also a subset of P1 union P2. Then P1 union P2 is called a refinement of P1 since all the points contained in P1, all the points of P1 contained in P1 union P2. Similarly, all the points of P2 contained in P1 union P2, therefore P1 union P2 is called the common refinement of P1 and P2. P1 union P2 is called the common refinement of P1 and P2. For an example, that P1 is equal to set 1, 3, 5 and P2 is equal to set 1, 2, 4, 5. These are two partitions of a closed interval 1, 5. P1 and P2 are partitions of a closed interval 1, 5. Then P1 union P2 is equal to 1, 2, set 1, 2, 3, 4, 5. It is also a partition of closed interval 1, 5. P1 is a partition of closed interval 1, 5. P2 is also a partition of closed interval 1, 5. Then P1 union P2 is also a partition of closed interval 1, 5. Here P1 subset of P1 union P2. Similarly, P2 is also a subset of P1 union P2. Then we said that P1 union P2 is the common refinement of P1 and P2 on closed interval 1, 5. P1 and union P2 is the common refinement of P1 and P2 on closed interval 1, 5. Here we learn about partition and partition points and refinement of partition. Next, subintervals. These subintervals, let's say x0, x1, etc., etc. are the partition of the closed interval A, B. Let's say partition points of the closed interval A, B. The set P is equal to set x0, x1, etc., xn with the partition of the closed interval A, B. Then closed interval x0, x1, closed interval x1, x2, closed interval x2, x3, closed interval x3, x4, so on. Closed interval xn minus 1, xn are called subintervals of closed interval a comma b. Here, total n plus 1 partition points. x1, x2, etc. xn are n partition points. x0 plus x0. Then we have n plus 1 partition points. Using n plus 1 partition points, we can form n subintervals. Using n plus 1 partition points, we can form n subintervals. It is denoted by I1, I2, I3, etc. In. That is, I1 is equal to closed interval x0, x1. I2 is equal to closed interval x1, x2. I3 is equal to closed interval x2, x3. So on. In is equal to closed interval xn minus 1, xn. Okay. Here P is equal to set x0, x1, xn is the partition of the closed interval a comma b. Then using these n plus 1 points, we can form n subintervals which are x0, x1, closed interval x0, x1, x1, x2, closed interval x2, x3. So on xn minus 1, xn, which are denoted by I1, I2, I3, etc. In. Next, length of the subintervals. Length of the subintervals. Here, P is equal to set x0, x1, etc. xn is the partition of the closed interval a comma b, and I1 is equal to closed interval x0, x1. I2 is equal to closed interval x1, x2. I3 is equal to closed interval x2, x3. So on. In is equal to closed interval xn minus 1, xn are the subintervals of the closed interval a comma b. Then length of I1. Length of I1 is equal to x1 minus x0. Here I1 is equal to closed interval x0, x1. Then length of I1 is equal to x1 minus x0, which is denoted by delta 1. Next, length of I2 is equal to x2 minus x1. Length of I2 is equal to x2 minus x1, which is denoted by delta 2. Third subinterval is I3. Here, length of I3 is equal to x3 minus x2, which is denoted by delta 3. Last, length of In. In is equal to closed interval xn minus 1, xn. Then length of In is equal to xn minus 1, which is denoted by delta n. Okay. Next, consider the closed interval 2, 7. Consider the closed interval 2, 7. Here, 2, 4, 6, 7 are partition points. Here, 2, 4, 6, 7 are partition points. When P is equal to set 2, 4, 6, 7 is a partition of closed interval 2, 7. Here, set 2, 4, 6, 7 is a partition of closed interval 2, 7. Here, subintervals are, first subinterval is closed interval 2, 4. Second subinterval is closed interval 4, 6. Third subinterval is closed interval 6, 7, which is denoted by I1, I2 and I3. Here I3 is the closed interval 2, 4. I2 is the closed interval 4, 6. I3 is the closed interval 6, 7. Then length of I1 is equal to, length of I1 is equal to 4 minus 2. Length of I1 is equal to 4 minus 2 equal to 2. And the length of I2 is equal to 6 minus 4, that is equal to 2. Length of I3 is equal to 7 minus 6, that is equal to 1. Here length of I1 is denoted by delta 1. Therefore, delta 1 is equal to 2. Length of I2 is denoted by delta 2. Therefore, delta 2 is equal to 2. Then length of I3 is denoted by delta 3. Therefore, delta 3 is equal to 1. Okay. Here 2, 4, 6, 7 are partition points. 2, closed interval 2, 4, closed interval 4, 6, closed interval 6, 7 are subintervals of closed interval 2, 7, which are denoted by I1, I2, I3. Then length of I1 is equal to 4 minus 2 is equal to 2. Length of I2 is equal to 6 minus 4 is equal to 2. And the length of I3 is equal to 7 minus 6 equal to 1. And the length of I is denoted by delta 1. Therefore, delta 1 is equal to 2. Length of I2 is denoted by delta 2. Therefore, delta 2 is equal to 2. Length of I3 is denoted by delta 3. Therefore, delta 3 is equal to 1. Here we learn about partition points, refinement of partition, next subintervals and length of subintervals. Okay. Next, upper sum and lower sum. Very important definition. Let us consider a bounded function f maps closed interval a comma b into capital R. R means set of real numbers. Okay. Consider a bounded function f maps closed interval a comma b into capital R. Here P is equal to set of A is equal to x0, x1, so on, xn is equal to b is the partition of the closed interval a comma b. Then I1 is equal to closed interval x0 comma x1, I2 is equal to closed interval x1 comma x2, and I3 is equal to closed interval x2 comma x3, so on. In is equal to closed interval xn minus 1 comma xn are n subintervals of closed interval AB corresponding to P. Here f is a bounded function. What is bounded function? Sin x is a bounded function. Sin x is a bounded function. Cos x is a bounded function. Sin x, maximum value of sin x is 1. Minimum value of sin x is minus 1. Values of sin x lies between minus 1 and plus 1. Therefore, sin x is a bounded function. Okay. And cos x is also a bounded function. Since the maximum value of cos x is 1, minimum value of cos x is minus 1, it is a bounded function. Let us see. Here, examples of bounded function. First, cos x. This is the graph of cos x. Its maximum value is 1 and the minimum value is minus 1. Maximum value 1 is called the supremum and minimum value minus 1 is called the infimum of this bounded function. Maximum value of cos x is 1 and the minimum value of cos x is minus 1. Therefore, cos x is a bounded function. Next, here sin x. Sin x is also a bounded function. Since its maximum value is plus 1 and the minimum value is minus 1. Okay. Values of sin x lies between minus 1 and plus 1. Then it is also a bounded function. Another example. Here f of x is defined in the interval, closed interval a comma b. F of x is a function. F of x is a function which is defined in the interval a comma b. Its maximum value is m. Its maximum value is m. Its minimum value is here. It is smaller. Minimum value of f of x is smaller. When f of x in this interval lies between capital M and small m. F of x lies between capital M and small m. In this interval, x is a bounded function. F of x is a bounded function. M less than or equal to f of x less than or equal to capital M. Then f of x is a bounded function. Here m is called the supremum and small n is called the infimum. Okay. Here we already defined bounded function f maps post integral a comma b into capital R. That is a bounded function from post integral a comma b into capital R. Then I1, I2, etc. In are and subintervals of closed integral a comma b corresponding to the partition P. Then f is bounded in every subinterval of closed interval a comma b. If f is bounded in closed interval ab, then f is bounded in every subinterval of a closed interval a comma b. Okay? Let us see. Here, let M1, capital M1 be the supremum of f over the first subinterval I1. I1 is the subinterval, M1 is the maximum value of f over the first subinterval I1. M1 is the maximum value of f over the first subinterval I1. Let M2 be the supremum of f over the second subinterval I2. Let M2 be the supremum of f over the second subinterval I2. And M3 be the supremum of, that means maximum value of f over the third subinterval I3. Etc. Mn be the supremum of f over the nth subinterval In. Mn be the maximum value of f over the nth subinterval In. Then we know that length of I1 is equal to x1 minus x0, which is equal to delta 1. Length of I2 is equal to x2 minus x1, which is equal to delta 2. Length of I3 is equal to x3 minus x2, which is equal to delta 3. So on. Length of In is equal to xn minus 1 equal to delta n. Then M1 into x1 minus x0. What is M1? M1 is the supremum of f over the first subinterval. M1 is the supremum of f over the first subinterval. M1 into x1 minus x0. X1 minus x0. X1 minus x0 is the length of the first subinterval. Okay. M1 is the supremum of f over the first subinterval. X1 minus x0 is the length of the first subinterval. Plus next M2 into x2 minus x1. M2 is the supremum of f over the second subinterval. M2 is the maximum value of f in the second subinterval. X2 minus x1 is the length of second subinterval. Plus M3. M3 is the supremum of f over the third subinterval. M3 is the supremum of f over the third subinterval. And x3 minus x2. X3 minus x2 is the length of the third subinterval. Etc. Last Mn. Mn is the supremum of f over the nth subinterval. And xn minus xn minus 1 is the length of the nth subinterval. Is said to be upper sum, and it is denoted by u of p comma f. M1 into x1 minus x0 plus m2 into x2 minus x1 plus m3 into x3 minus x2 plus etc. plus mn into xn minus 1 is said to be upper sum, and it is denoted by u p comma f. That is, upper sum is equal to m1 into, upper sum is equal to m1 into delta 1. Delta 1 means length of I1, x1 minus x0 is delta 1 plus m2 into x2 minus x1 is the delta 2. Therefore, m2 into delta 2 plus m3 into x3 minus x2 is equal to delta 3 plus so on plus mn into delta n. Next, let small m1 be the infimum of f over the first subinterval I1. What is infimum? Least value of minimum value of f over the first subinterval I1. M2 be the infimum of f over the second subinterval I2. M2 is the minimum value of f over the second subinterval I2. And M3 be the infimum of f over the third subinterval I3. And so on. Mn be the infimum of f over the nth subinterval In. That is, Mn is the minimum value of f over the nth subinterval In. We know that length of I1 is equal to x1 minus x0 delta 1, length of I2 is equal to x2 minus x1 equal to delta 2, and length of I3 is equal to x3 minus x2 equal to delta 3, and so on. Length of In is equal to xn minus 1 equal to delta n. Here, m1 into x1 minus x0 plus m2 into x2 minus x1 plus m3 into x3 minus x2 plus so on mn into xn minus 1 is said to be lower sum and it is denoted by L of P, F. That is m1 is the infimum of f over the closed interval x0, x1. M2 is the infimum, means minimum value of f over the closed interval x, x2. M3 is the minimum of f over the closed interval x2, x3, etc. Mn is the minimum value of f over the nth subinterval, that is closed interval xn minus 1, xn. This sum is said to be lower sum and it is denoted by L of P, F. That is L of P, F. P is the partition, F is the function defined on the closed interval a, b is equal to L of P, F. That is lower sum is equal to m1 into delta 1. What is delta 1? Delta 1 is equal to length of I1, that is x1 minus x0 plus m2 into delta 2. Delta 2 is equal to x2 minus x1 plus m3 into delta 3. Delta 3 is equal to x3 minus x2 plus etc. plus mn into delta n. Delta n is equal to xn minus 1. Okay, this is the lower sum. Next, examples of upper sum and lower sum. This is very important. Here, P is equal to A is equal to x0, x1, x2 equal to B is the partition of the closed interval a, b. Here, x0, x1, x2 is the partition of the closed interval a, b. Okay. Here, length of I1 is equal to x1 minus x0, which is denoted by delta 1. Length of I1, that is I1 is the sub-interval x0, x1. I2 is the sub-interval x1, x2. Then length of I1 is equal to x1 minus x0 and length of I2 is equal to x2 minus x1. Length of I1 is denoted by delta 1 and length of I2 is denoted by delta 2. Length of I1 is denoted by delta 1 and the length of I2 is denoted by delta 2. Okay. A and B are A is equal to x0, x1, x2 equal to B is the partition of the closed interval a, b. A and B are real numbers and A less than B. Here I1 and I2 are sub-intervals. Length of first sub-interval is equal to x1 minus x0. Length of first sub-interval is equal to x1 minus x0, which is equal to delta 1 and length of I2 is equal to x2 minus x1, which is equal to delta 2. Then M1 is the supremum of f of x in the interval x0 x1. M1 is the supremum, that is M1 is the maximum value of f of x in the interval x0 x1. Okay, M2 is the maximum value of the of a f in the interval x1 x2. M1 is the maximum value of f of x in the interval x0 x1, and M2 is the maximum value of f of x in the interval x1 x2. Here length of this interval is delta 1 and length of this interval is delta 2. Then upper sum is equal to M1 into delta 1 plus M2 into delta 2. Once again, here x0, x1, x2 are the partition points. P is equal to set x0, x1, x2 is the partition of the closed interval a comma b. First subinterval is I1, second subinterval is I2. I1 is equal to closed interval x0, x1. I2 is the closed interval x1, x2. Length of I1 is equal to delta 1. Length of I2 is equal to delta 2. Then M1 is the maximum value of f of x in the interval x0, x1. And M2 is the maximum value of f of x in the interval x1, x2. Then M1 into delta 1 plus M2 into delta 2 is equal to upper sum, that is u of p comma f. Then we get, listen here, we get area of this region. We get area of this region. Here M1 is the supremum of this f in this subinterval x0 to x1, and M2 is the infimum of f over this subinterval. Then M1 into delta 1 is the area of this rectangle. M1 into delta 1 is the area of this rectangle. We know that area of the rectangle is the length into breadth. M1 is the length of this rectangle and delta 1 is the breadth of the rectangle. Then M1 into delta 1 is the area of this rectangle. Okay. Next, M2 is the supremum of f over this subinterval x1, x2. Here M2 is the maximum value of f2. Here M2 is the length of this subinterval. Here M2 is the length of the subinterval, and delta 2 is the breadth of the subinterval. Delta 2 is the length of this subinterval. Then M2 is the length of this rectangle, and delta 2 is the breadth of this rectangle. Then area of this rectangle is M2 into delta 2. Then u of p comma f, that is upper sum, is equal to M1 into delta 1 plus M2 into delta 2. Once again, listen. M1 is the length of this rectangle and delta 1 is the breadth of the rectangle. Then area of this rectangle is M1 into delta 1. And M2 is the length of this rectangle and delta 2 is the breadth of the rectangle. Then area is the equal to M2 into delta 2. Then M1 into delta 1 plus M2 into delta 2 is the area of this region, this shaded region, that is the upper sum. Here three partition points x0, x1, x2. We get the two subintervals x0, x1 and x1, x2. Length of the subintervals are delta 1 and delta 2, and M1 is the supremum of f over the first subinterval x0, x1. M2 is the supremum of f in the second subinterval x1, x2. Here M1 is the length of the rectangle, delta 1 is the breadth of the rectangle, then M1 into delta 1 is the area of the rectangle. And M2 is the length of the rectangle, delta 2 is the breadth of the rectangle, M2 into delta 2 is the area of the rectangle. Then we get M1 into delta 1 plus M2 into delta 2 is the area of the two rectangles, these two rectangles. That is area of this region. This is called the upper sum. U of P, F. Here only, observe, here only 3 points and 2 rectangles. Okay. Next, here consider 6 partition points. Here we consider 6 partition points. X0, X1, X2, X3, X4, X5. There are 6 partition points. Using these 6 partition points, we can form 5 subintervals. Using these 6 partition points, we can form 5 subintervals. And length of first subinterval I1, length of first subinterval I1 is equal to x1 minus x0, which is equal to delta 1. Length of second subinterval is equal to x2 minus x1, which is equal to delta 2. Length of third subinterval I3 is equal to x3 minus x2. Length of fourth subinterval x4 minus x3, which is denoted by delta 4. Length of fifth subinterval x5 minus x4, which is denoted by delta 5. And M1 is the supremum of f of x over the interval x0, x1. M2 is the supremum of f of x over the interval x1, x2. M3 is the supremum of f of x over the interval x2, x3. M4 is the supremum of f of x over the interval x3, x4. And M5 is the supremum of f of x over the interval x4, x5. Then upper sum is equal to M1 x1 minus x0 plus M2 x2 minus x1 plus M3 x3 minus x2, M4 x4 minus x3 plus M5 x5 minus x4. That is M1 delta 1 plus M2 delta 2 plus M3 delta 3 plus M4 delta 4 plus M5 delta 5. That is the upper sum. Here M1 is the supremum of f over the first subinterval. Here M1 is the length of the rectangle, first rectangle, and delta 1 is the breadth of the rectangle, first rectangle. Then M1 into delta 1 is the area of the first rectangle. Next, M2 is the length of the first rectangle, delta 2 is the breadth of the second rectangle. Okay, sorry, M2 is the length of the second rectangle, delta 2 is the length of the second rectangle. Then area is equal to M2 into delta 2. Next, here M3 is the length of the third rectangle and delta 3 is the breadth of the third rectangle. Then M3 into delta 3 is the area of the third rectangle. Next, M4 is the length of the fourth rectangle and delta 4 is the breadth of the fourth rectangle. Then M4 into delta 4 is the area of the fourth rectangle. Next, M5 is the length of the fifth rectangle, delta 5 is the breadth of the fifth rectangle. Then M5 into delta 5 is the area of the fifth rectangle. Then upper sum is equal to M1 delta 1 plus M2 delta 2 plus M3 delta 3 plus M4 delta 4 plus M5 delta 5 is the area of this region. Here, how many partition points? 5 partition points. Okay, 5 partition points. Then next, Here 9 partition points. 9 partition points. T is equal to set x0, x1, x2, etc. xn be the partition of the closed interval a comma b. Here length of I1 is equal to delta 1, length of I2 is equal to delta 2. We know that length of I3 is equal to delta 3. So on length of I8 is equal to delta 8. Then M1 is the supremum of F over the first subinterval x0, x1, M2 is the supremum of F over the second subinterval, etc. M8 is the supremum of F over the 8th subinterval. Then upper sum is equal to M1 into x1 minus x0 plus M2 into x2 minus x1 plus M3 into x3 minus x2, so on M8 into x8 minus x7. That is Q of P comma F is equal to M1 delta 1 plus M2 delta 2 plus M3 delta 3 plus etc. M8 delta 8. Then we get 8 rectangles. First rectangle, area is M1 delta 1, second is area M2 delta 2, third area M3 delta 3, so on. Last rectangle's area M8 delta 8. Here we get area of upper sum means area of this region. Here partition points are 9. Then we get area of this region. Observe. Here partition points are 3. Then we get area of this region. Here partition points, how many partition points? 6 partition points. Then area decrease. That is upper sum decreases. Here total 9 partition points. Here also area upper sum decreases. Then number of partition points increases, upper sum will decrease. Important point. Number of partition points increases, upper sum will decrease. Next. Here, lower sum. Here, that P is equal to, set A is equal to x0, x1, x2 equal to B. Be the partition of the closed interval a comma b. Here x0, x1, x2 are the partition points and closed interval x0, x1 and closed interval x1, x2 are the sub-intervals. That is, it is denoted by I1 and I2. Length of first subinterval is delta 1, length of second subinterval is delta 2. Okay, length of first subinterval is delta 1, length of second subinterval is delta 2. Here M1, what is M1? M1 is the least value of f of x in the interval x0 to x1. M1 is the least value of f of x in the interval x0, x1. That means M1 is called the infimum of f of x in the interval over the interval x0, x1. And M2 is the infimum of f of x over the interval x1, x2. M2 is the infimum of f of x over the interval x2, x1, x2. Then lower sum is equal to M1 into x1 minus x0 plus M2 into x2 minus x1. That is LPF is equal to M1 delta 1 plus M2 delta 2. M1 is the infimum of F over the first subinterval. Delta 1 is the length of the subinterval. M2 is the infimum of F over the second subinterval. Delta 2 is the length of second subinterval. Okay. Then we can find here. M1 is the, what is M1? M1 is the infimum. Here M1 and delta 1 are length and breadth. Then we get area of this rectangle. Here M2 and delta 2 are length and breadth. Then we get area of this rectangle. then L of P comma F is equal to M1 delta 1 plus M2 delta 2. Then we get area of these two rectangles, area of these two regions over the interval AB. Okay. Next, let P is equal to x0, x1, x2, etc. x5 is the partition of the closed interval A comma B. Here 6 partition points. Here 6 partition points. Using 6 partition points, we can form 5 subintervals. We can form 5 subintervals: x0, x1, x1, x2, subinterval x2, x3, subinterval x3, x4, and x4, x5. Here, M1 is the minimum value of F over the first subinterval, and M2 is the minimum of F over the second subinterval, and M3 is the minimum of F over the third subinterval. M4 is the minimum of F over the fourth subinterval, and M5 is the minimum of F over the fifth subinterval. Okay, then lower sum is equal to M1 into x1 minus x0 plus M2 into x2 minus x1 plus M3 into x3 minus x2 plus M4 into x4 minus x3 plus M5 into x5 minus x4. This is the lower sum, which is denoted by L of P comma F equal to M1 into delta 1. Delta 1 is equal to x1 minus x0. M1 delta 1 plus M2 delta 2 plus M3 delta 3 plus M4 delta 4 plus M5 delta 5. That is the lower sum. Here we get the area of these 5 rectangles. Area of these 5 rectangles. M1 is the infimum of F over the first subinterval. Here M1 is the length of the rectangle, and the delta 1 is the breadth of the rectangle. Then M1 into delta 1 is the area of this rectangle, and 2 into delta 2 is the area of this rectangle, and 3 into delta 3 is the area of this third rectangle, and 4 into delta 4 is the area of the fourth rectangle, and M5 into delta 5 is the area of the fifth rectangle. Then lower sum is equal to area of these 5 rectangles. Here partition points are 6. Here partition points are 6. Here partition points are 3. Okay. Next, here partition points are, here 9 partition points, x0, x1, x2, etc. x8. There are 9 partition points. Then we get 8 subintervals. Here total 9 partition points. Then we get 8 subintervals. x0, x1, x1, x2, so on, x7, x8. F1 is the infimum of f of x over the first subinterval. M2 is the infimum of f of x in the second subinterval. M3 is the infimum of f of x in the third subinterval. So on, M8 is the infimum of f the last subinterval. Then lower sum is equal to M1 into M1 is the infimum of f over the first subinterval. X1 minus x0 is the length of first subinterval. Then lower sum is equal to M1 x1 minus x0 plus M2 x2 minus x1 plus M3 x3 minus x2, so on, M8 x8 minus x7. That is L of P comma F is equal to M1 delta 1 plus M2 delta 2 plus etc. M8 delta 8. Then we get area of these rectangles. Then we get area of this rectangle. Here M1 into delta 1, the area of the first rectangle. M1 into delta 1 is the area of the first rectangle. M2 into delta 2 is the area of the second rectangle. So on, M8 into delta 8 is the area of the eighth rectangle. Then L of PF is the area of this region. That means area of these 8 rectangles. Then here partition points, number of partition points increases, lower sum is also increases. partition points increase, number of partition points increases, lower sum is also increases. Number of partition points increases, upper sum is decreases. Okay. Number of, listen here. Here, only 3 partition points. Observe the area of the rectangles. L of E, F. Here, how many partition points? Here, 6 partition points. Here, L of PF. This is the area of the rectangles. Lower sum. Here, 9 partition points. This is the lower sum. L of P, F. Here, partition points, number of partition points increases, lower sum also increases. And then when partition points, number of partition points increases, upper sum decreases. Then what happens? Here, important definition, upper and lower Riemann integrals. Lower Riemann integral of f on closed interval AB is defined as supremum of lower sum L of P, F, where P belongs to closed interval A, B, and it is denoted by integral A bar to B f of x dx. Lower Riemann integral means supremum of L of P, F, supremum of lower sum. And upper Riemann integral of f on closed interval AB is defined as infimum of upper sum. Supremum of lower sum is known as lower Riemann integral. It is denoted by integral A bar to B f of dx. And infimum of upper sum. Infimum of upper sum is known as upper Riemann integral of f, and it is denoted by integral A to B bar f of x dx. Okay. Then lower Riemann integral is supremum of L of PF. Upper Riemann integral is infimum of L of PF. Okay. Then last one, Riemann integral. Last one, Riemann integral. What is Riemann integral? A bounded function f is said to be a Riemann integral, simply R integral on closed interval AB if its lower and upper Riemann integrals are equal. Lower and upper Riemann integrals are equal. Upper sum and lower sum. Upper sum and lower sum are equal. Means supremum of lower sum and infimum of upper sum are equal. We say that is Riemann integral. The common values of this Riemann integral of f on closed interval AB is denoted. The common value of this integral is called Riemann integral, and it is denoted by integral A to B f of x dx. If upper and lower Riemann integrals are equal, we say that the common value of this integral is said to be Riemann integral of f on closed interval A, B, and it is denoted by integral A to B f of x dx. That means we get the area under the curve f of x between 2 points or between a closed interval A, B. Thus we get the area of a region under the curve f within the closed interval A, B. Here number n we are called the lower and upper limits of Riemann integration. Okay. Here another example. Here this is the graph of a parabola. It is defined on the closed interval -2 to 3. Closed interval -2 to 3. Here upper sum is 12.5625. Area is 10.833. Lower sum is 9.3125. Here lower sum is less than true value of this area of this region. True area of this region, which is less than or equal to upper sum. If upper sum and lower sum are equal, we get the correct area of this region. That is the Riemann integral. Integral A to B f of x dx. Okay.
Thank you, ma'am. Thank you so much. It was actually a highly informative class for all of us. Usually in mathematics, when we hear the term integration, presently we are all faced as a difficult with integration. So now, am I audible now?
Yes, ma'am.
Yes, audible.
Okay. So you have explained the concept of this Riemann integration in a step-by-step way. Without going directly into that topic, you have explained each and every simple concept. For example, partition of closed interval, then refinement of that partition, upper sum, lower sum, everything in a very simple way. We are dealing with the students. We don't have the parent department for mathematics. We deal with the students of physics, chemistry, and computer science students. So I'm damn sure this session was highly informative for them. So ma'am, thank you so much. And now the session is open for discussion. I think the participants can make their queries now. Students, if you have any doubt, participants, you can ask it now. Yes, Kirtana M, you can ask now. Kindly unmute it.
Good evening, ma'am. ഞാൻ കീർത്തന ഫസ്റ്റ് ഇയർ BSc Chemistry ആണ്. Ma'am, could you please explain about the real life application of Riemann integral?
In mathematics, it is used to find the area of base. In physics, chemistry, so many applications are there. നമുക്കത് ഡിസ്കസ് ചെയ്യാം. നിങ്ങൾക്ക് ഇതിൻ്റെ അകത്ത് നോക്കിയാൽ ഒരുപാട് ആപ്ലിക്കേഷൻസ് കാണാൻ പറ്റും റിയൽ ലൈഫിൽ. സാധാരണ നമ്മളുടെ മാത്തമെറ്റിക്കലായിട്ട് പോവുകയാണെങ്കിൽ നമ്മൾ ഏരിയ വോളിയം ഇതൊക്കെ കാണണമെങ്കിൽ നമുക്ക് ഇതിന്റെ റീമാൻ ഇൻഡിക്കേഷൻ യൂസ് ചെയ്യാം. ഇൻഡിക്കേഷന് ഒരുപാട് ആപ്ലിക്കേഷൻസ് ഉണ്ട്.
Okay, ma'am. Thank you.
Nivedita, please.
Good evening, ma'am. Ma'am, I'm Nivedita of first year BSc Physics. My question is there any drawbacks of Riemann integral?
ഹിയർ ഞാൻ ഡിഫൈൻ ചെയ്തിട്ടുള്ളത് ഒരു എഫ് ഓഫ് എക്സ് സീറ്റ് വളരെ സിമ്പിൾ ആയിട്ടുള്ള ഒരു എക്സാമ്പിൾ ആണ്. എഫ് ഓഫ് എക്സ് സീറ്റ് എക്സ് ഇസ് ദ സ്ട്രേറ്റ് ലൈൻ. കേർവ് ഞാൻ എടുത്തിട്ടുള്ളത് എഫ് ഓഫ് എക്സ് സീറ്റ് എക്സ് എന്ന ഒരു സ്ട്രേറ്റ് ലൈൻ മാത്രമാണ്. നമ്മൾ സാധാരണ ലാസ്റ്റ് ഞാൻ കാണിച്ചു പാരബോള ഒക്കെ കാണിക്കുമ്പോൾ അതിന്റെ സബ് ഇന്റർവൽസ് ആയിട്ട് എടുക്കുമ്പോൾ എക്സാക്ട് വാല്യൂ കിട്ടാൻ കുറച്ച് വിഷമമാണ്. ദാറ്റ് ഈസ് ദ ഡ്രോബാക്ക്. കൃത്യമായിട്ട് അത് മാത്രമല്ല പാർട്ടീഷൻ എന്തായിരിക്കണം, ഈക്വൽ ഇന്റർവൽസ് ആണെങ്കിൽ മാത്രമേ നമുക്ക് എക്സാക്ട് വാല്യൂസ് കിട്ടുള്ളൂ. പാർട്ടീഷൻ ഈക്വൽ അല്ലെങ്കിൽ നമുക്ക് എക്സാക്ട് വാല്യൂ കിട്ടാൻ കുറച്ച് വിഷമമാണ്. ദാറ്റ് ഇസ് ദ ഡ്രോബാക്ക്.
Okay, ma'am. Thank you.
So I think no more questions now. So I would like to invite Ms. Nandita Yu, from Assistant Professor from Department of English, to deliver the vote of thanks.
Good evening, everyone. Honorable Resource Person, Dr. Mookambika A.P, Respected Principal, Dr. Sujesh C.P, IKC Coordinator, Srimati Chandini P.M, our Webinar Coordinator, Dr. Bhavya B, all teachers and our enthusiastic participants. I'm honored to get an opportunity to express my gratitude on behalf of Department of Mathematics. Today,
We are extremely fortunate to have Dr. Mookambika A.P. as our resource person. The discourse about the geometric interpretation of Riemann integral enhanced our understanding of this topic. The talk was really informative, insightful, and educating. In lieu of Department of Mathematics, I express my sincere and heartfelt thanks to our speaker, Dr. Mookambika A.P. Thank you, ma'am. Thank you for being a part of this webinar series.
Thank you.
Welcome, sir. I extend my gratitude to our principal, Dr. Sujay C.P., who is rendering unwavering support to this webinar series. Thank you, sir. I also express my sense of gratitude to our IQAC coordinator, Srimati Chandini PM, Assistant Professor, Department of Computer Science. Thank you, ma'am. The young and dynamic chair, Dr. Vinny K., Assistant Professor, Department of Physics, made the session so interactive. Ma'am, thank you for making the day. Ms. Anashwara M., Assistant Professor, Department of Mathematics, who is the energy behind the realization of this session. I convey my gratitude to you, ma'am. I extend my sincere gratitude to Dr. Bhavya B., Assistant Professor, Department of Physics, the coordinator of Guruvachan2023 for your constant support. Thank you, ma'am. And I also express my sincere thanks to all our participants who have been participating as the cornerstone of this event. Thank you. Thank you.